I was hoping I'd see more of you. Please tell your friends to come. We are beginning a new phase of our journey in this class, and we're going into the realm of the uncertain. If you thought the realm of the certain was fun, wait till we go into unknown territory. As you hopefully know, I'm Babak. I'd like to be called by that, not by Professor, Doctor, Mr., Sir, or any of that stuff. And I want to orient you to my teaching style in the class. It's more interactive. In fact, I'm very interactive in the class. So one of the things I want you to do is get used to talking to your neighbors and getting to know them a bit better. Maybe after some time you get to cluster around the same set of people when you come to lecture. A lot of the questions that I ask you, I will give you some time to work with each other and try to crack and tackle those problems, and then we'll have some subset of you in any given lecture to answer some of those questions. By hopefully Tuesday or Thursday of next week, I would like to have a volunteer who is, they don't even know what they're volunteering for, they're raising their hand. There's no extra credit for this one. I'd like to have a volunteer who will be the first person I will point to when I pose the first problem in the lecture. What that means, you have to know what you're getting into before you raise your hand. So what that means is that if in any given lecture I call on you and you're not there, the whole world and YouTube is going to know that you missed and ditched the lecture that day. In exchange for that sacrifice, you have, or the volunteer will have, the option of taking that first question or passing it on to somebody else roughly half the time. Okay, I don't want that person to take every single first question, because then the rest of you will know that volunteer will take the first question, and you may not give that first question your best. So you may get picked. Okay, one thing I have changed in my habits over the years is that after the group discussions, if you got picked, you were on the spot. But I've altered that, so I've softened it up a bit. What I'd like you to do is, as you are discussing with the folks around you how to solve the problem, also discuss who is going to answer that question if a member of your group is selected. So let's say you're in a group of 3 people, and somebody in your group is selected. We shouldn't have to waste time after you are selected trying to figure out which one of you is going to answer the question. Decide on that a priori. So this way, if you're on the extreme edge of shyness and you really don't want to talk, you won't be forced to talk, and one of the other members of your group will answer the question. Was that fairly clear? I hope so. So here's what I want you to do. I want you to talk to the folks in your neighborhood, exchange names, phone numbers maybe, social security numbers, mother's maiden name, whatever it takes to break the ice. Make sure you're talking to each other, because you'll be doing a lot of that in the session. Calling all Canadian geese. I actually paid for that for these lectures. All right, so let us begin. So in this phase of the class, we're going to introduce to you a formalism that allows you to deal with or make some sense of uncertainty in life. There are a lot of things that are uncertain. If you're a stock trader, for example, you'd like to know what the probabilities are that after you go long on a stock, that price of the stock is going to go up, or if you're short in the stock, the price of that stock is going to go down. If you're playing cards, you'd like to know what the probabilities are that you're going to win the particular hand you have. There are a lot of experiments. There are a lot of situations in life that we can formalize or model using the principles of probability. So at the heart of probability theory is what we call, hey, what's going on here? A random experiment. By the way, this is the other thing I'm going to be probably introducing a change in how you perceive these lectures. I'm a blackboard kind of guy. If this room had a blackboard, I'd be with 1-inch chalks writing on the board. So I try to simulate as much of that as possible. I insist on writing most of the time. There might be times when I show diagrams, but I insist on writing because I want to keep the pace at a level that you can follow. So you may want to start bringing notes or notepads to class. Oh, thank you. Yeah, I'm proud of being a Luddite in that sense. So, okay. So we have at the core a random experiment. Okay? It's some kind of a phenomenon or process whose outcome you can't know with certainty. So the outcome is uncertain. Outcome uncertain. But, let me clarify that. Which outcome occurs is uncertain, so which outcome is uncertain, but set of outcomes is known. What do I mean by that? Outcomes is known. This is a new tablet for me, so if my handwriting is a bit off, I hope you forgive me. I'll try to do more practice and get this down cold. So, we have a collection of possibilities that we call outcomes of the experiment. We don't know which one will occur, but we know what that set is. For example, suppose I roll a die. Okay? Do you know what number is going to turn up? I can't hear you. No. But do you know what the possible outcomes are? Yes. Okay. What are they? 1, 2? 1, 2, 3, 4, 5, 6. Okay. Ouch. Where did it go? Off screen. 1, 3, 2, 1, 1, 2. Come on, 4. I got $20 on you. This die only has 1, 2, 3. So you know the outcomes of the experiment, huh? I had to snatch these back from my 4-year-old. She was refusing to give them back. I said, I need it for class. Okay, but roll of a die, a normal, ordinary, well-behaved die, has outcomes that we can list. Whoops, not 6. and put in a set that we call, with the lovely symbol omega, and this is our sample space. What is a sample space? Well, it has certain properties. A sample space is the finest grain set of items that satisfy a couple of properties. One is that they are mutually exclusive and collectively exhaustive set of outcomes, or a finest grain set, I don't need to say set again, of outcomes. So notice the numbers 1 through 6 represent the totality of outcomes. They are mutually exclusive, which means what? When I run a trial of the experiment, when I roll the die once, what does mutual exclusivity mean? Yeah. If one happens, you know that none of the others happened. Right? They can't. Two of those elements in my set omega cannot occur simultaneously in the same trial. So they're mutually exclusive, and they're collectively exhaustive. What does that mean? What does it mean that the elements in omega are collectively exhaustive? Yeah, the outcome of the experiment is always some element in that set. In other words, there's no way I can run the trial, run the random experiment, or roll the die in this case, and get a number that's different from 1 to 6, given that I know that it's a 6-sided die and properly numbered. Okay? So that's at the core of our model. There's a sample space. It's got elements. Those elements are the finest grain, collectively exhaustive, mutually exclusive set of outcomes. Now, one of the things I'm going to do today is, question. Finest grain means that the outcome will not, I can't break apart any of those elements and have an outcome that's embedded in it. So that's in contrast to something else that I will define, which is an event. An event is a subset of omega. So, for example, I can say one of the outcomes of the experiment is that the die landed on an even number, right? So that is an event. That is not a sample point. By the way, each of these elements is called a sample point. Okay? So a collection of sample points is an event. So one event, for example, as I said, is that the die will end up showing an even number. Okay? So that would consist of the numbers 2, 4, and 6. That would be an event. That is not a finest grain outcome of my experiment. Okay. So one thing I'm going to do is spend some time getting you used to different ways of visualizing and drawing outcomes of experiments. This is a craft. Not all drawings are created equal. Depending on the experiment, certain forms of drawing the outcomes of an experiment will lead to more insight, or will give you more insight than others. And drawing should become part of your important toolbox tools to attack probability problems. So let's talk about a few examples. So let me say I flip a coin. Okay, normal, ordinary, fair coin. Okay, actually, I don't even care if it's fair or not, because right now we're not talking about the likelihoods of these outcomes. All we're talking about right now is what those outcomes are of a random experiment. So I flip a coin, and I've got how many outcomes? How many sample points? 2. And so flip a coin. And those outcomes are heads or tails. That's one way to draw the random experiment. I only have 2 outcomes, so one is with a branching tree. Another way, of course, is to write heads or tails. Now, depending on what you want to do, one might be better than the other. For example, if all you want to do is just have a listing of the outcomes, or say, in a more complicated example, how many what the size of your sample space is, how many sample points are in there, then you might just want to list it as a set. But if you want to put probabilities on these outcomes, then the branching one is probably a better one, because I can put probabilities on each of these branches. So if I have a fair coin, I will assign a 1/2 to each of those branches and say, okay, the probability of a head is 1/2 and the probability of a tail is 1/2. Now suppose I change this a bit and I say, let's go to another one, and say I flip 2 coins, or independently of each other, I flip a coin twice. How would you draw how many outcomes do I have? Talk to each other and come up with a drawing for this. How would you graphically represent this experiment? Okay. I'll take a volunteer. You are? What's your name? Jay. Okay. So I have the first coin that's let's say I'm flipping a single coin twice, and the result of the second toss has nothing to do with the result of the first toss. Okay. So I have 2 outcomes for the first trial. What should I label this? I'm going to put a subscript here because I want to specify that this head occurred on the first flip or by coin 1. Okay, and now what? Okay, for each of them I draw another 2 branches. So I'm not labeling the final points yet. I'm going to do that labeling of the sample points out to the right. This one is simply going to be H2, which means that on the second flip, a head occurred. And then this one would be tail 2, H2, tail 2. Okay? Now, can you give me a reasonable listing of the outcomes? So now we know that we have 4 outcomes, right? So how should I label those outcomes? Let's say here, I'm going to let's use a different color. What should I label this outcome? H1, H2. H1, T2. T1, H2, and T1, T2. Okay? So that's one way to represent two flips of a coin. Another way, can somebody tell me another way? Actually, why don't you finish it, Jay? Yeah, H1, H2, H1, T2, T1, H2, T1, T2. And I'll tell you about yet another one, which is sometimes helpful, which is like this. So this is the outcome of first coin, first toss. And this is the second toss. So in the first toss, I either have a head or a tail. In the second toss, I either have a head or a tail. And then each of these boxes will be labeled the same way that we did the other ones. So this one would be H1, H2. This one would be T1, H2. This one would be H1, T2, and T1, T2. Now, if I were to change the problem and say I'm rolling a die twice, or I'm rolling two dice, which one of these would you prefer? Would you do it with the tree? Or would you do it with the rectangle? Or the square? Which one's easier? The square. Right? The square is easier. So, two dice. Two six-sided dice. What I would do is I would simply draw a square and hope I'm dividing it properly. What do I have? 1, 2, 3, 4. There we go. That was saved. And then 1, 2, 3, 4. One more. Okay. So I've got the outcome of 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I have a total of 36 outcomes. My sample space is of size 36. And each of these blocks represents a sample point. Now, we talked a little earlier about an event. So let's say I define, first let me define an event for you. Any subset of the sample space is called an event. A is an event. So you take any subset of the sample space, you have an event on your hand. How many events can I define on this set? Let's see how Satish taught you combinatorics. Talk to each other. How many events do I have in a sample space of size n? So let's say omega is of size n. How many events can I define? Okay. Do I have a volunteer? What's your name? Parat? Go for it, Parat. Okay, so the answer is 2 to the power n. Now talk to me about a more insightful path of getting to that 2 to the n. How did you get to 2 to the n? So you're saying out of n, I have subsets of size 1, I have subsets of size 2, I have a subset of size n, and this is equal to 2 to the power n. What about a subset of size 0? We have to add that too. Okay. This, in fact, is an identity. K from 0 to n of n choose k is 2 to the n. But I'm still stuck. My 7th grade brain is still stuck at this. Why? I like your method. You're systematically breaking down the possible outcomes into mutually exclusive sets. Events of size 0 or events of size 1 don't have an overlap with events of size 2. Either an event is of size 1 or it's of size 2 or some other number. Right? So it is true that if I count all of the, and I know how to count them. I know how many subsets of size 2 I have. It's n choose 2. I know how many subsets of size k I have. It's n choose k. And if I add up all of these, I should get the answer I want. But why is that answer 2 to the n? That's right. So every element that I'm looking at, as I'm going through the different sample points, I have n sample points in my set. For every element, I'm making a binary choice. Either I'm going to include that in the particular subset that I'm looking at or trying to construct, or I will exclude it from that subset. So there's a binary choice associated with every single one of the elements in my set. And because of that, this number on the left-hand side, the summation on the left-hand side, must equal 2 to the n, because I have 2 to the n possibilities. You can think of it as a binary string, where each element in each bit on the binary string corresponds to a particular sample point. If a bit is 0, that means that particular sample point didn't make it into this particular subset that I'm looking at. If it's 1, it means it made it into that subset. So we have 2 to the n possible subsets in our 2 to the n events defined. And the set of all possible events is called an event space. Okay. Let's see. So we have a flavor of how to draw things, and actually I want to give you one more example. Everything that we've done so far has been finite. Let me give you an example that takes you into a different realm. I will come back to talk about this stuff in terms of continuous probability later on. I want to focus on discrete events and random events. So let's say I'm flipping a coin, and I keep flipping until I get my first head. Fair enough? I keep flipping until I get my first head. Can you draw that sample space for me? So whoops, I want it to be green. Flip a coin. I don't care if it's fair or not. Flip a coin until first head. Then stop. Draw the sample space for this. Well, don't just stare at the board, at the screen. You got to be talking to each other. I want the decibel level to go up here. Okay. I'll take another volunteer. Today is the day of volunteers. Don't get used to it. Yeah. Okay, but help me draw it, Jack. So, first trial. Well, you have to give me both possibilities. So I need to plot. Pardon me? 2. Okay, I'm going to draw 2. Either it's going to be heads or tails. Now what? So if I end up at heads on the first trial, on the first flip, I'm done. I stop. I only continue flipping if I get tails on the first flip. And what are the outcomes for the second flip? H2 and T2. Very nice. And I keep doing this. H3 and T3 and so on. There is no end to it. You might go 1,000,000 flips and not get your first head. It's unlikely, but it can happen. Okay, so this is a drawing of my sample space. Now, what are my sample points? Can you tell me how to write some of the elements, Jack? H1. T1, H2. Very nice. H3, and so on. Okay? I can't emphasize enough the importance of drawing these things and learning how to use the appropriate kind of graphical representation so that you gain insight on how to solve probability problems. Later on, we will put probabilities on these and talk about the probability that I will have to wait n flips before I get my first head. Okay? And if you draw it like this, you can just read the answer off the diagram. There's not a complicated set of things you have to do. Basically, it would be, okay, if my coin is fair, I'd put 1/2 probability on each of these. And if I ask you, what's the probability that I get my first head on the third flip, you will say 1/2 times 1/2 times 1/2. And if I change this to P and then this 1 minus P, you will say I have a 1 minus p times 1 minus p times p. That would be the probability of getting heads on the third try. Instead of heads or tails, you can have successes or failures. How many tries before my first success? It all depends on the context. This is an example of a binomial random variable that we will talk about later in the class. So the single coin flip is Bernoulli. It's a Bernoulli trial. It's got one of two possible outcomes, and each of those outcomes will have its associated probability or likelihood. And you can concatenate them and have a sequence of such trials and talk about probabilities of those kinds of random phenomena. Okay. So I've been murmuring something about probability, but I haven't really talked to you about what that is. You have an intuitive notion of probability. It's the likelihood of something happening or not happening. So let's formalize that in a cleaner way. So what is probability? Probability is essentially a function from the event space to the set of reals. So probability is a function from the event space to the reals. It gives you a numerical value. You give it an event, it spits out a number. Now, remember, events can be single sample points. So when I talk about event spaces, that includes the possibility that something that you're trying to find the probability for happens to be the finest grain outcome of the experiment. Now, okay, so this is a function. It takes something in my event space and spits out a number, but it can't just be an arbitrary function. It must satisfy certain axioms. And that's where we talk about the axioms of probability. So it's a function that has the following properties. Let's call this axiom 1. For any event A, P of A, the probability of event A must be greater than or equal to 0. Duh. This is called by the intuitive name of non-negativity axiom. Let me see if you can fill in the next blank. The probability of the sample space is one. The likelihood that something inside my sample space will occur is 1. Why? Because the sample space is by definition collectively exhaustive. There is no outcome that is not in my sample space. Okay? I know this sounds funny that we're actually writing axioms down, but I hope the fact that these axioms don't violate your intuition about what likelihood should mean is going to carry you through the boring axioms here. A third one, and I'll introduce this in a baby version first, and then we'll deal with some of the complications later. By the way, this second one has its own name. It's called the normalization axiom. Next week, when we get to conditional probability, and I will talk about the experiment having occurred and we know that the outcome is somewhere within a particular subset of the sample space, your universe, your sample space shrinks, and you have to normalize all the properties so that in your new conditional space, everything adds up to 1. Okay? Basically, the second property says, in your universe of possible outcomes, the probabilities must add up to 1. The third and last axiom is that if A1 and A2 are two events that are mutually exclusive, in other words, if A1 occurs, we know for a fact that A2 did not occur, then the probability of A1 union A2 is equal to, I'm not saying they're complements of one another, they're just PA1 plus PA2. Let's draw this so that it's a little clearer. So here's my sample space. We use Venn diagrams quite a bit in this class. That's another way, by the way, you should get used to identifying events or drawing outcomes. So let's say I have two, this is my sample space, the rectangle. I have an event A1 and I have an event A2. Okay? These two events are mutually exclusive. Whoops, not that color. Oh, no, okay, you get the idea. Let me see, that's bugging me now. There we go. A1 and A2 are mutually exclusive, so the probability of their union is the sum of their probabilities. These are the three axioms. So any probability function that you define on your sample space has to satisfy these axioms. There is some weakness in this last one in that it cannot handle the last experiment that I described for you, flipping a coin until the first heads. Because in that one you have a countably infinite set of possibilities in your set. But it turns out that the generalization to an infinite, countably infinite set is valid for discrete events. We'll let mathematicians worry more about that. Okay, so three axioms. The simplest one, and they're all fairly straightforward and shouldn't violate your intuition. You've essentially seen the fact that any event has a non-negative probability is something we would expect. The fact that all of the probabilities added together should add up to 1 is not too hard to fathom. And the last one, perhaps when you studied sets and you studied the numbers of elements in different sets, that should not come as a surprise to you either. So if you have two sets that are mutually exclusive, the number of elements in their union is what? I have a set A1 with its own size, and I have a set A2 that doesn't have an overlap with A1, that has its own size, N2. The size of their union is what? N1 plus N2. So the same applies to probabilities. Okay. Now, let's talk about let's do some examples. So here's one example. I have a bag, and in this bag I have two red balls. I have one green ball, and I have 5 blue balls. 3, B4. Hey, where'd you go? What in the world? B1, B2, B3, B4, B here. Okay, there we go. Now, they're all the same size. I can't see inside the bag. I stick my hand in the bag and I pull a ball. What's the probability that I will pull the ball labeled red 1? I will give you a lot of trick questions, but this is not one of them. One what? 1 out of 8. That's only one of the possibilities, right? They're all equally likely to be selected. They're all the same size. They all have the same surface texture. I can't tell one from the other by sticking my hand in the bag. So I'm equally likely to pick any of the balls. In other words, the probability law that I'm defining on this experiment is a uniform probability law. Every single sample point has the same probability as any other sample point. And I've got 8 sample points. Okay? What's the probability that I will pull a red ball? Why is it 1/4? I've got 2 red balls and a total of 8 balls in my sample space. So notice here, I am essentially dividing the size of the set consisting of the sample point R1 over the size of my sample space, which is 8. Here, I'm dividing the size of my event R1 and R2 over the sample space size. So the event red, the outcome red is an event. It's not a sample point. And what's another thing you recognize? That the probability of red or green or blue is what? 1. This is the same as the probability of red plus the probability of green plus the probability of blue, and that's 1. I've taken you one step beyond axiom 3. Axiom 3 only told us that if you have 2 mutually exclusive events, you can add up their probabilities. So how do we go from 2 events to 3 events or to any arbitrary finite number of events? Talk to each other a bit. This is what I'm asking you to sort out. True or false? If AK and AL have no overlap for K not equal to L, is it true that probability of A1 union A2 union all the way to AN is equal to the probability of A1 plus the probability of A2 plus the probability of AN? Start looking at it from when you have only 3 sets. If you sort that out, then the other extension is not that difficult. First, agree on whether this is true or false. Okay. What's the answer? Is it true? Yes. So let's deal with it in the case of 3 events. So let's say I have 3 events that are mutually exclusive. How do I argue that this is, so A1, well, I won't clutter the screen by saying they're mutually exclusive. We already are aware of that. So how do I proceed? Okay. So let's draw this. I've got A1. Huh? They're supposed to be what? I'm sorry? Oh, the union. I'm sorry. Yeah. This is a union. Thank you. And I have 3 mutually exclusive events, A1, A2, and A3. Yeah, I'm going to coalesce these 2 sets as one. So I write probability of A1 union A2 union A3. So what do you know about, before I apply the third axiom, what do you know about the red set here, the union of A2 and A3 and A1? They're disjoint. So because A2 union A3 intersection with A1 is the empty set, we can apply axiom 3 and write this as PA1 plus what? PA2 union A3. And then the next step is straightforward. We simply apply axiom 3 to the second term on the right-hand side. So I have PA1 plus PA2 plus PA3. And you can extend this to n sets. So basically we exploited the associativity of union. I grouped A2 and A3 together. That's what I did. And then I applied axiom 3. If I had n sets, I would start, I would go through a progression of smaller and smaller unions until I get all the terms I want. Okay. So that's that. Now, from these axioms, we can infer a whole bunch of stuff. For example, some results. So if I have an event A, then I define as the complement of event A anything that's not an A. Right? That's the definition. And this is my sample space. What can you tell me about the probability of A in terms of the probability of A complement or vice versa? Can you express the probability of A in terms of the probability of A complement? Oh, everybody talk. Well, I'll ask. So talk to each other and see what you can come up with. And I forgot to label this, although it shouldn't be a surprise. This property is called the additivity. Additivity axiom. Okay, so what's the probability of A in terms of probability of A complement? Yeah. 1 minus. Why? So this is, wrong color. It's 1 minus the probability of A complement. Why is that? So A union A complement is the sample space, okay? So pause for a moment. What I'm trying to get you to get used to, you've been doing a lot of proofs up to this point in the class, okay? This is child's play compared to what you've been doing so far. What I'm trying to get you to do is to start building some of these results from the first principles being the 3 axioms. I want to use the 3 axioms to derive a whole bunch of other results. This one happens to be a very powerful result because we use it in simplifying our probability calculations. So far, we've noticed that A and A complement, their union is the universal set, or the sample space. Now, how do I bring in probability into this? What if I apply probability to both sides? The probability of the left-hand side is what? Actually, the probability of the right-hand side is what? Is 1. By axiom 2. By the normalization axiom. The probability of the sample space is 1. How can I massage the left-hand side? By what? I can't hear you. Oh, it's union. I'm sorry. I keep doing this. A union, A complement. Sorry about that. I didn't clean that up. A union, A complement. The probability of A union, A complement is what? How do I figure it out? Yeah. Third axiom. A and A complement are mutually exclusive, so the probability of their union is, so this is by axiom 2, and this is by axiom 3. And so I have the 2 probabilities adding up to 1, which means the probability of A is 1 minus the probability of A complement. Now this sounds quite pedestrian and totally, hopefully, intuitive, but it has important ramifications. For example, let's say I flip a coin 1,000 times. Okay? I flip a coin 1,000 times. Or pick whatever number you like. And I ask you, what's the probability that I get at least 1 head? Talk to each other. Okay. How would you crack this? Okay, so pause for a moment. So we look at the complement event. The complement event is that after you flip the 1,000 coins, you have seen no heads. They're all tails. Okay? So let's delete this. This is okay, and then what do I do? Yeah, this is 1 minus the probability of no heads. Notice if you wanted to tackle this problem directly, you would have had to do a pretty nasty counting computation, right? Because you would have to say the probability of exactly 1 head, the probability of exactly 2 heads, the probability of exactly 3 heads, all the way to the probability of exactly 1,000 heads, and you had to add up all those numbers. Not fun. But instead, we looked at the complement. The complement of that event is that I flip this coin 1,000 times, I get no head whatsoever, and that's easy to compute. What is that number, do you think? Fair coin. 1/2 to the 1,000. Yeah, they're independent flips. Every time I get a tail, it happens with probability 1/2, and I keep multiplying along the tree diagram, and I get 1/2 to the 1,000. I subtract it from 1, and that's the answer. Okay? Notice this is a large number. This is on the scale of 0 to 1, it's a large number. It's pretty close to 1. Because if you flip a coin 1,000 times, the likelihood that you'll get no heads is very small. And that's represented by 1/2 to the 1,000. Okay. So this relationship between the probabilities of complementary events will come in handy in many problems. All right. Now, let's talk about another situation. Suppose I have an event B and I have an event A that is a subset of B. Okay? If that's true, what do you think the relationship is between the probabilities of these two events? What does your intuition say? Yeah. Pardon me? Less than or equal to. If an event B subsumes an event A, its likelihood is at least as big as A. Now let's see if we can work from first principles to establish this result. So I'm going to define the space here outside of A but inside of B as with the symbol B \A. This, oops. Oh no, what happened? Where'd you go? All apps. Okay. The world lives on. Okay, so B \A is the complement of A in B. In other words, the part of B that's not included in A. Can you express B in terms of these two sets? What is going on here? Maybe it's because my hand is a little wet. Okay, so can you express
the probability of B as the probability of some union. Don't stare at me. Stare at your neighbor. More hair is not going to grow on my head by you staring at my head. You're just going to experience glare. Okay, what's the answer? This is the probability of what union what? Oh, you just answered. Anybody else? Yeah. A union B backslash A. And you can express this how now? Probability of A plus the probability of B backslash A. Why can I do that? Because what? Third axiom, because they're mutually exclusive. The way I defined them, I made them mutually exclusive. And now how do I show that the probability of A is less than or equal to the probability of B? Non-negativity axiom. So now I isolate P of A. That's what I'm after, right? So P of A is P of B minus P of B backslash A. The non-negativity axiom says this is this is greater than or equal to 0. So I'm subtracting a non-negative quantity from the probability of B, which means the result I get must be less than or equal to the probability of B. I have the probability of B. I'm subtracting something non-negative from it. So at most what I'm going to get is the probability of B. And this property is called, go away. So if A is a subset of B, then P of A is less than or equal to P of B. This is called the monotonicity property. Monotonicity property. Can you use this property to show? So actually I'll do it as a true-false. True or false? The probability of any event A is less than or equal to 1. Not a trick question. What's the answer? Everybody. True. Well, how do we show it? Yeah. You. Don't look the other way. Yeah. So you're going through the same derivation that we went through to get the monotonicity property. Use the monotonicity property directly. Now you can use it. What's the relationship between A and the sample space? It's a subset of omega. Therefore, P of A is less than or equal to the probability of omega, and you know probability of omega is 1. So now we have uh-oh. Did I just lose it? Oh, okay, good. So this is less than 1. Now I want to go up. So the first axiom said that the probability of any event A is non-negative. Now we've arrived at the result that the probability of an event A is less than or equal to 1. So the probability of any event is between 0 and 1. And we built all of this from our basic axioms, even though
And none of this should be surprising to you. But apparently it was to one of my students back at MIT. In the first time I was TAing the probability class there. This is back in the mid-90s. We spent the whole 1/3 of the class telling students probability is a number between 0 and 1. And the first exam comes, and a whole bunch of people made some mistakes calculating the probability of event A, and when they would get some ridiculous number, they would say, I must have made a mistake. Sorry, I don't have time to go and fix it. But not this one kid. There was one guy who wrote, the probability of event A should be and is 6. And it caused about a 15-minute disruption in the grading session because we just couldn't stop laughing. So please let that not happen to you. If you get a number that's not between 0 and 1, at least have the humility to say, I made a mistake. I don't have time. Given more time, I would be able to figure it out. But here you go. Do the best you can with the grade. All right. So that's that. And then I have a couple other results building on top of what we've studied, and then I'll let you guys go. There's this other thing called the law of total probability. And the best way to understand that is through a Venn diagram. So here's my sample space. You've got to be kidding me. I have a brand spanking new computer here, and it's giving me a hard time. Okay, here we go. Let's start normally. All right. Lost some. Law of total probability. And we've got, suppose I split my sample space into a set of events that are collectively exhaustive and mutually exclusive. Okay? So CK intersection with CL is 0, is the empty set if K and L are not equal. And the union of the CKs, K equals 1 to N, is my sample space. Fair enough? So I've partitioned my sample space into a set of N mutually exclusive, collectively exhaustive events. One way, for example, would be I roll a die. What's two events could be the probability that the outcome is an even number, the probability that, or an even number is the outcome, an odd number is the outcome. So in that case, I have two of these complementary sets. Now, if I now have an event, I want that to be a different color. If I define an event A in this universe, this event A will have some kind of overlap with these different sets, or the partitioning sets C. With some of them, it may not have an overlap at all, but here, for example, would be the overlap of A with C1, and similarly for all the other ones. Can you write or tell me what the probability of A is with respect to the probability of its intersection with each of these? I've got to figure out why this is happening. Can you tell me what the relationship is between the probability of A and the probability of each of these intersections? Without doing much work, just look at the diagram and tell me, based on what we've just derived here. So this
purple region here is A intersect C1. The corresponding region here would be A intersect C2. What? What do I have to do with all these individual probabilities? Add them up. Yeah. If I add these up, I get my answer, because A can be written as the intersection of A and C union intersection of A and C2 union all the way to the intersection of A and Cn. And these are all mutually exclusive sets. So I can write... Oh! Time to go! So I can write the total probability as the sum of the individual overlaps. That's called the law of total probability. I'm going to use that next time to derive the probability of a union when the two sets do overlap. Okay? And then we'll take it from there. See you later. Hi.
So if the question is